In this video, we'll talk about the domain and range of a function. Let's start by defining the domain and range of a function. Recall that a function is a rule that assigns to each input exactly one output. We call the collection of all inputs the domain of the function, and we call the collection of all outputs the range, or the image of the function. We think of the function as a kind of machine. It takes elements of the domain and converts them into elements in the range. When I use the word element, I simply mean an object inside the set. So A, B, and C are elements of the domain. That means that they're members of the set. X, Y, and Z are elements of the range. Again, that means that they're members of the set or that they're included in the set. A function is like a machine, and it takes elements from the domain and it converts them using some rule into elements of the range. Let's talk a little bit about naming conventions. It is common to give names to functions, and standard choices are f, g, and h. We like to pick f for function because f is the first letter of function, but really we can use any letter we want so long as it isn't being used for something else. It's also common to use letters to denote objects in the domain and the range. Frequently we use x as the input variable, something in the domain, and y as the output variable, something in the range. But as with functions, you can use any letter so long as it isn't being used for something else. However, I do want to give you a word of caution. Try to avoid using letters for things in the domain or range that are usually used for other things. For example, you probably don't want to use f as a symbol for the input variable, because f usually stands for a function, so if f is suddenly a variable, you might confuse yourself. So let's talk a little bit about the terminology. So suppose that we have a function that we're calling f, and x is the input variable and y is the output variable. In that case, we like to write y equals f at x as a way to indicate that y is given by a function of x. So x in this case is the input and y is the output. So y equals f at x is just a way of writing down that y is determined by x using the function f as the rule. F is what converts x into y. Because the value of y depends on the choice of x, we call y the dependent variable. And in this case, we call x the independent variable. Because nothing is forcing a value on x, it's independent. But once you have an x, that determines the y. Y depends on x. That's why it's called the dependent variable. It is common in mathematics to call objects in a set elements, as I mentioned already. So if x is in the domain of a function, we might say that x is an element of the domain. And similarly, we might say that f at x is an element of the range. Remember, f at x is y in this case. Y is an element of the range. When we say that x is an element of some set, we just mean that it's an object inside of the set or a member of the set, but it's normal to call those elements in mathematics. We have a special notation for that as well. If x is an element of a set D, where D is maybe the domain of a function, then we write this to mean x is in the set D, or x is an element of D. We write x and then this symbol and then D. So we read that as x is an element of D, or x is in D. This symbol looks the way that it does because it started out life as the Greek letter epsilon. So we started with the Greek letter epsilon, so you would say that x epsilon d means that x is an element of d. So we're thinking of epsilon as being the first letter of element, or e, really. X is an element of d, and then just over the years, this symbol epsilon evolved to look like this. But it just means that x is an element of d. X is in the set D. For the most part, we're interested in functions from and to sets of numbers. So how do we write out the domain or range of such a function? If there are finitely if there are finitely many elements in a set, you just list them out. Just write them down. Usually, though, that won't work for the functions that we're interested in because there are just too many elements to list. So there are two standard ways to write out sets of infinitely many numbers. One is what we call set builder notation, and the other is interval notation. We'll talk about both of these. So let's start with set builder notation. Set builder notation is a method of specifying the elements of a set in terms of certain conditions. So we write a set in this way. So we use braces to indicate, or curly brackets as sometimes people call them. We use these braces to indicate that everything inside the braces is in the set. So we read this as saying that the set is the set of all elements x such that state some condition about x is true. So this vertical bar should be read as such that. So this vertical bar right here this is read as such that. So when we're trying to construct a set, we look at all of the x values such that some statement about x is true. And if that statement about x is true, then that x goes into the set. So it's much easier to see if we're looking at an example. So here's our first example. This set, this is the set of x's such that x squared is equal to 4. That means that this set contains all x's so that the condition x squared equals 4 is true. That equation is true precisely when x equals 2 or x equals negative 2. So what that means is the set of all x's such that x squared is equal to 4 is the set of all x's such that x is equal to 2 or x is equal to negative 2. Since there are only finitely many of these, we don't need to use the set builder notation. We can just write them out. X equals negative 2 or x equals 2. So the set of all x's such that x squared is equal to 4 is the same as the set containing the two numbers negative 2 and 2. You can see since there are finitely many, we can just write them out. We put them in these braces to indicate that we're looking at a set. Braces mean a set. Commonly, we'll be using set builder notation to describe intervals, although there is another notation for that. So an interval is a collection of numbers that lie between two endpoints. So for example, the interval strictly between 3 and 8 contains all numbers larger than 3 but smaller than 8. In set builder notation, we write it in this way. So it's the set of all x's such that 3 is strictly less than x, which is strictly less than 8. This contains all of the numbers strictly between 3 and 8. So it contains all numbers between 3 and 8, not just integers. So it contains fractions, and it contains numbers like pi. Pi is approximately 3.14, so it's slightly bigger than 3. That means it's in this set. The words strictly between indicate that we don't want to include the endpoints. And that corresponds to this strict inequality. 3 is strictly less than x. That means we don't allow x to be equal to 3. And x is strictly less than 8. That means we don't allow x to be equal to 8. It's strictly between. If you want to include the endpoints, one or both of the endpoints, then you can replace the strict inequality with this symbol, which means less than or equal to. This first symbol that we were talking about, this is read as strictly less than. But this symbol is read less than or equal to. As an example, we have this set here. This is the set of all x such that 3 is less than or equal to x and x less than 8. So this is the set of all numbers between 3 and 8, including 3, but not including 8. 3 is less than or equal to x. So that means 3 could be equal to x. X could take on the value 3. However, x is strictly less than 8, so x cannot be equal to 8. So that's why it's including 3, but not including 8. The other way of writing intervals is to use what we call interval notation. And this is a shorthand notation to make it much easier to write intervals. So as the name suggests, we use interval notation to denote intervals. For example, if you want to write down the set of numbers between 5 and 13, not including the endpoints, you could write it down this way. This is what we call interval notation. We use a parentheses to indicate the endpoints. So 5 is the endpoint, and 13 is the other endpoint. And we put them in parentheses to indicate that we're looking at all of the numbers between them, but not actually looking at 5 or 13. So in set builder notation, we would write it this way. So we're looking at the set of all x's such that x is strictly between 5 and 13. We write that this way. So as I mentioned, we use parentheses to indicate that we don't include the endpoints. Now if you want to include the endpoints, then you replace the parentheses with brackets. So if you want to include the left endpoint, then replace the left parenthesis with left bracket. So for example, this set, so we have bracket 5, 13 parenthesis. That is the set of all x's such that x is greater than or equal to 5, or 5 is less than or equal to x, and x is strictly less than 13. So this first inequality is less than or equal to. That means x is allowed to be equal to 5, so we want to include 5, so that's why we use a bracket. On the other side, x is strictly less than 13, so we want to exclude 13, so that means we use parentheses. You use brackets if you want to include the endpoint, and you use parentheses if you want to exclude the endpoint. Similarly, we just talked about the left endpoint, including the left endpoint. But if we want to include the right endpoint, then we can replace the right parenthesis with the right bracket. So here we have the set from 5 to 13, excluding 5, but including 13. And in set builder notation, that's the set of x such that 5 is strictly less than x, and x is less than or equal to 13. Less than or equal to 13 means we're including 13, so that's why we use a bracket. The bracket means we're including the 13. The parenthesis means we're excluding the 15 or the 5. Excuse me. The parenthesis means we're excluding the 5. 5 is strictly less than x. That means x can't equal 5. So that's why we use a parenthesis. Now if you want to include both 5 and 13, then you'd use brackets for each. So bracket 5, 13 bracket, this is all of the numbers between 5 and 13, including the endpoints. So in set builder notation, we write it like this. It's the set of x such that 5 is less than or equal to x is less than or equal to 13. So 5 is less than or equal to x, so that means x can be equal to 5, so we're including 5. And x less than or equal to 13 means x could equal 13, so we include the 13, we use a bracket. When we use this symbol less than or equal to, keep in mind that there's an or there. X could be less than 13 or equal to 13. Less than or equal. So in general, if a is a number smaller than b, so a is strictly less than b, then the interval with parentheses, parenthesis a comma b parenthesis, this is the interval of all numbers between a and b, excluding both of the endpoints a and b. If you use parentheses for both, you're excluding both. Bracket a comma b parenthesis means you're looking at the interval between a and b. So you're including all of the numbers between a and b, but you're including a, but you're not including b. Parenthesis means that you're not including it, so you're excluding b. The interval parenthesis a comma b bracket, this is the collection of all numbers between a and b, and also b. Parenthesis means we're excluding A. Bracket means we're including B. Now here we have brackets on both sides. Bracket A comma B bracket. That's the interval of all numbers between A and B, including both A and B. Now the first interval here, where we don't include any of the endpoints, this is known as an open interval. Open interval. And the bottom one, where you include both, this is called a closed interval. So if you don't include either of the endpoints, then it's open. It's like an open-ended interval. It doesn't include the ends. So it's called an open interval. And if you use these brackets, then that means you're including both of the endpoints, and so we call that closed. The two in the middle here, we don't call those closed or open. Those are neither closed nor are they open. One thing that we can do is we can replace b with infinity. So let's look at the first one here. If we replace b with infinity, then the interval has no largest number. So parenthesis a comma infinity parenthesis is the collection of all numbers greater than a. So this is an interval starting at a and just increasing without bound. So that means it includes all of the numbers greater than a. So it's the set of x's such that x is greater than a. Notice that this is strictly greater than a, so we use a parenthesis here. So we could, of course, include a. So if we wanted, we could put a bracket here. A comma infinity equals the collection of x's such that x is greater than or equal to a. That would be fine. You can include a. What you can't do is include infinity. Infinity is not a number. It's just an indication that it's growing without bound forever and ever. So you can't include infinity because it isn't an actual thing. So that was if we replaced b with infinity. It's also possible to replace a with infinity. So if you replace a with not infinity, but rather negative infinity, so if we replace a with negative infinity, then in the first one, for example, you just replace a with negative infinity, and then you have the interval from negative infinity to b. This means you have an upper bound of b, but you include all of the numbers smaller than b. So this interval from minus infinity to b is the collection of all x's such that x is less than b. It's all numbers less than b. Notice it's strict inequality. X is not equal to b, so we have a parenthesis here. And of course you can replace it with a bracket. Minus infinity to b bracket. This is the collection of all x such that x is less than or equal to b. So you can include either of the endpoints a or b. Now what you can't do is include infinity or negative infinity. So under no circumstances should you have a bracket next to infinity. Infinity isn't a number. It's just an idea indicating that something is either growing without bound or, in this case, decreasing without bound. Now one thing you can do is you can have infinity in both places. So note, you can have parenthesis minus infinity to infinity parenthesis, and this is the set of all numbers. The set of all numbers, or real numbers as we call them. So if you see this is the collection of all numbers between minus infinity to infinity, so it's everything. It's all real numbers. So here's a little chart giving you a summary of the interval notation, and it just describes all of the things that we've mentioned. For example, this first one, this is the interval from a to infinity. It's the collection of all x's greater than a, which we write this way in terms of an inequality, x greater than a. You can write the graph on the number line this way. Notice again we're including a parenthesis here because the parenthesis is telling us that we're not including a. A is not included. So you just have a parenthesis and then you draw a line with an arrow indicating that it just goes forever. So then down here, this is the interval that contains x greater than or equal to a. So we have a bracket there. So the graph on the number line, you just change the parenthesis, you change this parenthesis to a bracket to indicate that you're including a. And then you draw the arrow, you draw this line with an arrowhead to indicate that you continue going. Now if you're including a, that's x greater than or equal to a. And so we have similar things here with negative infinity, and then here are these finite intervals that don't go off to infinity. So if you're looking at the interval from a to b, but not including either endpoint, that's a strictly less than x, strictly less than b. You write it with parentheses, and here, notice on this number line, we draw a line from a to b to indicate all of the numbers between a and b, and we use parentheses here to indicate that we're not including the endpoints. If you want to include an endpoint, you just change the parenthesis to a bracket. If you want to include both endpoints, you just use both brackets like this. Something we'd like to do is we'd like to find the domain of a function. To determine the domain of a function, it's usually easier to ask what isn't in the domain. So we ask ourselves, are there any values that cannot be inputs? So you want to look for the following. If there is a denominator, that denominator cannot be 0. If there is a square root, or more generally an even root, then the thing underneath the radical should not be negative, because we can't take square roots of negative numbers and still get a real number. So let's look at an example. So we want to identify the domain of the function you see here. F at x equals 1 over x squared minus 9. This is a fraction. So what we want is we want to make sure that the denominator should not equal 0. So in order to determine the domain of this function, it's easier to ask what cannot be in the domain. And what we don't want is we don't want the domain to equal 0. So we want x squared minus 9 to not equal 0. So what values are excluded? So we exclude any x such that x squared minus 9 equals 0. So we just need to solve this for x. We're solving for x not to find what x is, but to find what x cannot be. So we want x squared minus 9 to not equal 0. So x squared minus 9 equals 0. Just add 9 to both sides. So then we have x squared equals 9. So now we can compute the square root of both sides. So x is going to be equal to plus or minus the square root of 9. So what does that mean? X is equal to plus or minus 3. So that means we're excluding x equals 3 and x equals negative 3. So the domain is the set of x such that x is not equal to 3 and x is not equal to negative 3. We can write this in interval notation, but it's not actually an interval. It's a few intervals. So if we tried to draw this on a number line, that line isn't straight. Let me try that again. If we plot this on a number line, we plot negative 3 and 3. Now, the domain is every number except for negative 3 and 3. So what we can do is we can draw an open circle like this for both of those. And then we draw a line. Let me just change the color here. Or let's just use a highlighter. So it's all of these numbers except for 3 and negative 3. So we're excluding 3 and negative 3. So in interval notation, we don't have one interval, we have 3 intervals. So the intervals are negative infinity to negative 3, not including negative 3, negative 3 to 3, not including either of the endpoints, and then 3 to infinity, again, not including the endpoints. Now, there is a shorthand way of writing this using what we call a union symbol. So we write it like this, minus infinity to minus 3, and then you put what looks like a U for union. Minus 3 to 3, and then a union symbol, 3 to infinity. So this symbol here, these are called union. And the union symbol is a way of combining two non-overlapping intervals, or two or more, in this case 3. So the way we understand this is that the x's that are allowed are x's in any one of these intervals. So it means that x can be in this interval, or it can be in this interval, or it can be in this interval. So you can think of this union symbol as meaning or. So x can be in the first set, or the second set, or the third set. So that's called a union. And this is the domain of the function here. It can be anything except for 3 or negative 3. So here it is in set builder notation, and here it is in interval notation. Let's do another example. Identify the domain of this function. So this is a square root. So you want to avoid having a negative number in the square root. So we want x minus 5 to be greater than or equal to 0. So it's fine if it's equal to 0. You're allowed to have the square root of 0. That's just 0. So note, square root of 0 equals 0. But square root of a negative number is not a real number. That's because there's no real number that I can square to get a negative 1. So that's why we want to make sure that this is greater than or equal to 0. Now if x minus 5 is greater than or equal to 0, then you can add 5 to both sides, and you just simply have that x is greater than or equal to 5. So this is the domain. So the domain is equal to the set of x such that x is greater than or equal to 5. Now in interval notation, this is bracket 5, comma, infinity, parenthesis. And that's the domain of the function. Okay, let's do another example. Identify the domain of the function that you see here. F at x equals 1 over the square root of x minus 5. Now this x minus 5 is what we were just looking at. So let's just scroll back. That's what we were just looking at. So because we have a radical in the denominator, we still have to make sure that everything inside the radical is positive or possibly 0, but it's in the denominator now, and so it can't be 0. So since the square root of x minus 5 is in the denominator, the square root of x minus 5, now it cannot equal 0. So that means x minus 5 has to be greater than 0. It has to be greater than or equal to 0 because of the radical. Since this is the square root of x minus 5, that means x minus 5 has to be greater than or equal to 0. But since it's in the denominator, that means it also can't be equal to 0. So that's why we don't allow the equals here. In the previous example, we had x minus 5 is greater than or equal to 0. Let's just go back. So here, we had the radical x minus 5. So x minus 5 had to be greater than or equal to 0, but that's because this is in the numerator. Down here, it's in the denominator. If it's in the denominator, that means that it can't be equal to 0. So not only does it have to be positive because of the radical, it has to be, or excuse me, let me say that again. Not only does it have to be non-negative because of the radical, it has to be strictly positive because we can't allow 0 in the denominator. So that means x minus 5 is greater than 0. Or in other words, if we add 5 to both sides, x is greater than 5. So the domain of this function is x such that x is greater than 5, which is, in interval notation, it's parenthesis 5 comma infinity parenthesis. So we had to exclude the endpoint 5 in this case because 5 would put a 0 in the denominator, and that's not allowed. What about this one? Here we want to identify the domain of the function f at x equals 1 divided by the square root of x squared minus 9. So as before, we want to avoid the denominator being 0, but also notice that we have a radical in the denominator. So the radical means that the thing inside the radical needs to be greater than or equal to 0. So the radical means that x squared minus 9 is greater than or equal to 0, but it's also in the denominator. So the denominator means that x squared minus 9 can't equal 0. So if you put those together, this means that x squared minus 9 is strictly greater than 0. So in order to figure out where x squared minus 9 is strictly greater than 0, it helps to look at when it's actually equal to 0. Maybe one way to do that is to factor the x squared minus 9. So if you factor this, this becomes x plus 3 times x minus 3 is greater than 0. X squared minus 9 is the difference of squares. It's x squared minus 3 squared. So we can write that as x plus 3 times x minus 3. Now this will be equal to 0 when x is equal to negative 3 or positive 3. So if I were to draw a number line, like so, I could put negative 3 here, and I could put 3 here. Now if I pick x equals negative 3 or 3, these will give you 0, which are not allowed. We need to have that the product, x plus 3 times x minus 3, needs to be strictly greater than 0. So in particular, it can't be equal to 0. So we have to exclude negative 3, and we have to exclude 3. Well, what about the rest of these intervals? If you pick anything between negative 3 and 3, what happens? Well, for example, what if you pick 0? Then you're going to have 3 times a negative 3, which is a negative number, which is not allowed. So nothing between minus 3 and 3 is allowed, because if you plug in any x between minus 3 and 3, you're going to get a positive number times a negative number, which is going to give you something which is negative. So anything here will give you a negative result, which is not allowed. However, if you pick x greater than 3, if you pick any x greater than 3, for example 4, then you're going to have 7 times 1, which is positive. So anything over here will give you a positive number. Similarly, anything to the left of negative 3 will give you a positive number. If you pick something smaller than negative 3, then you're going to have a negative number here and a negative number here. So if you multiply two negative numbers together, you're going to get something which is positive. So the domain is anything to the right of 3 or to the left of negative 3. So in interval notation, that tells us that the domain is, well, the domain, I guess if I'm using the word is, I don't need to write out equals. The domain is the set negative infinity to negative 3, excluding negative 3, and then union 3 to infinity. So remember that this, let me just redraw this. This symbol here, this is the union symbol. And it means that x can be in either one of the sets. So x can be in minus infinity to negative 3 or 3 to infinity. So the union symbol you should think of as meaning or. Now if we wanted to write this out in set builder notation, so in set builder notation, how would we do that? Well, there are different ways we could do it, but we could just simply say that it's all x such that x squared minus 9 is greater than 0. And that would already tell us what it is, but it's not very informative to write it that way because we don't really know what those x values are. It's much easier if we have inequalities like x less than negative 3 or x greater than 3. And so we can write it that way. So we can say that this is the set of x such that x is greater than 3 or x is less than negative 3. So this is a much more informative way of writing it. Because if you write it like this, it's not immediately clear what values of x are allowed. If you write it like this, then it's very clear. So this is just the same thing as writing it in interval notation like this. So the corresponding interval notation is negative infinity to negative 3, union 3 to infinity. And again, I'm using parentheses here because we have to exclude the endpoints. If you plug in x equals 3, you're going to get a 0 in the denominator. So we cannot include 3 or negative 3. So this is set builder notation. And this is interval notation. So this just tells you what I've already said earlier. So to write, that's supposed to be TWO. To write two disjoint non-overlapping intervals as a single set using interval notation, use the union symbol, which is just a stylized U, basically. So for example, the interval from 2 to 6 or 13 to 17. 2 to 6 union 13 to 27. So this is the set of all numbers that can be found in either 2 to 6 or 13 to 27. So again, you should think of this union as an OR. X can be in one set or the other. You're picking any of the x's, so it's any x such that comes from here or it could come from there. So let's talk a little bit now about piecewise defined functions. A function that uses different formulas for different parts of the domain is called piecewise defined, or a piecewise defined function. And the basic idea behind a piecewise defined function is just that you use a different rule for different values of the input. So here is an example. F at x is equal to, well, here's the graph that you see here. Now there are two different rules that determine the output, depending on where the input is. If x is less than or equal to 2, then the rule that you use is 2 minus x. And this is the graph of the line y equals 2 minus x. So y equals 2 minus x. But not for all x. It just lasts until you get to x equals 2. Because once you get to x equals 2, then you have to switch. So x equals 2 uses this rule. X equals 2, so notice that this is x less than or equal to. So if x is equal to 2, then you use this rule 2 minus x. But the instant that x is bigger than 2, you switch to a different rule, which is x minus 2 squared. That's this one right here. So this is the parabola y equals x squared shifted to the right by 2 units. So what you have is a function that is made up of 2 different pieces. And those 2 different pieces are 2 different rules. And which rule you use depends on where your x value is. So if x is less than or equal to 2, you use the first rule, 2 minus x. However, if x is greater than 2, then you use the second rule. So for example, so let's compute f at 3. So if we want to use f at 3, or if we want to use this rule to compute f at 3, that means that x is equal to 3. So you look over here and you say, okay, well, is x less than or equal to 2? No, it's not. So we rule this one out. It's not that one. X is equal to 3, it's bigger than 2, so we use this rule. So that means we use this rule, x minus 2 quantity squared. So it's 3 minus 2 quantity squared equals 1 quantity squared equals 1. So when x is equal to 3, y is equal to 1. Now, on the other hand, if you wanted to look at, for example, x equals 0, so f at 0, what rule would you use then? Well, if x is equal to 0, then x is less than or equal to 2, so you'd use this rule. So now it would be 2 minus 0, which is equal to 2. And that's this point right here. It has coordinates x equals 0 and y equals 2. So you have to be a little bit careful. Notice that the interval notation looks a lot like the point notation, so you just have to be careful. So here we're looking at a point, so there's no ambiguity. This can't be an interval. This is the point with x coordinate 3 and y coordinate 1, for example. Here's another example of a piecewise defined function. It's the absolute value function. Here we're calling it g. G at x equals the absolute value of x. The way that this function is defined is that whatever x is, it returns the positive version of it. So if x is positive, you just get x back. So we can write it out that way. G of x is equal to, so if x is positive, then you just get x back. Now on the other hand, if x is negative, then you don't get x because it's negative. So if x is negative, you get the opposite of x, which we write this way. Now you don't want to think of this as negative x, because x itself is negative. This is the opposite of a negative number, so it's positive. So when you see this symbol here that looks like a negative sign, it's actually saying the opposite of x. So if x is less than 0, that means it's a negative number. The absolute value function returns the positive version of x. So if x is less than 0, it's a negative number, so we want the opposite of x, which is positive. Now in terms of the graph, to the right of 0, we have y equals x. But to the left, we have y equals the opposite of x. What about at 0? Notice that I didn't include 0. Well, in this case, both of these are 0 at 0, so I could put that there. Or I could put that there, or both. Because when x is 0, both rules give you the same thing. G at 0 is equal to 0. So you could use either one of these. It gives you the same thing. So you could have both of them, or you could say that x strictly greater than 0 is x, and x less than or equal to 0 is going to be negative x. Or if you prefer, you could just do it this way. So now you're using the rule that g at x is equal to x for x greater than or equal to 0. So now you're including that on this part. So this point right here, now now it goes along with this piece right here. y equals x. It doesn't really matter because where the two pieces meet, you get the same value. That's not always going to be the case. Let's look at another example of a piecewise defined function. This one also uses the absolute value sign. So here, h of x is equal to, let me try that again, and again. I'm having some trouble with my pen here, as you can see. So if x is positive, then you just get the same thing again. So it's the square root of x if x is positive. However, if x is negative, then this absolute value sign returns the opposite. So if x is negative, then the absolute value sign gives you the opposite of x. So it's radical opposite of x. Now this might look a little funny because there's a negative sign underneath the radical, and we're always led to believe that it doesn't make sense to have the square root of a negative number. But we're not looking at the square root of a negative number here because x is the negative number. So this is the opposite of a negative number. So the opposite of x is a positive number, and the square root of that makes sense. So here we have y equals the square root of x to the right of 0, and y equals the square root of the opposite of x to the left of 0. What about at the origin? Well, again, they both meet there, so you can use either one. So let's just say that it's the square root of x if x is greater than or equal to 0, because the square root of 0 is just 0. But of course, the square root of negative 0 is also 0. So either one would do. Again, that's because where the two domains meet, you get the same thing, but that's not always going to be the case. Here's an example where that's not the case. A piecewise defined function can have as many pieces as you want. And here we have 3 pieces, but you can have as many as you like. So these things right here on the right, if x is less than or equal to 1, if 1 is less than x is less than or equal to 2, if x is greater than 2. These tell you which rule to use. So if x is to the left of 1, then that means you use the first rule. So f at x is x squared. If x is between 1 and 2, then that means you use the second rule. So if x is between 1 and 2, the output is always 3. If x is bigger than 2, then you use the bottom rule, and you just get x back. So f at 4 is just going to give you 4. 4, 4. So if you pick any x bigger than 2, then you're just going to get the y value is the same as the x, because this is y equals x here. And this is y equals x squared here. Y equals x squared here. And this is just y equals 3 right there. Now, if you're at an endpoint, you've got to be a little bit careful. So what if you're at 1? If x is equal to 1, you look at the rule. See, it's not going to be this one, because 1 is not greater than 2. We're looking at x equals 1. We're looking at x equals 1 here. So what rule do we use? Well, we don't use this rule. What about this one? You don't use this one. See, this middle rule, this is when x is strictly greater than 1 and less than or equal to 2. So you don't use this rule. So the rule you want to use is the first one. See, if x is equal to 1, you use this top rule because x is less than or equal to 1 for the top rule. So the idea is you're given an x, and you're trying to figure out what the output is. So you're given an x, and then you see, okay, well, where does this x lie? Does it lie greater than, is it greater than 2? No. Is it between 1 and 2? No. Is it equal to 1? Yes. X is less than or equal to 1. So that means we use the first rule. So if x is equal to 1, you get 1 squared, which is 1, which is what you see here. 1, 1. So that's represented in the picture by using a filled-in circle. So the filled-in circle means that that's your value for your output. Notice that here we have an empty circle. So x is equal to 3 when, or rather f at x is equal to 3 when x is between 1 and 2, including 2 but excluding 1. So to indicate that on the graph, you're including x equals 2, so you have a solid circle over here, a filled-in circle. On the other hand, you're excluding 1. So when you exclude 1, you have an open circle like this. You have an open circle. Now it's important that one of those circles be filled and one be empty, because if both of these circles were filled, if I was to try and put in some color here, like if I was to fill that in, notice now I don't pass the vertical line test. So if I have both of those circles filled in, then it doesn't pass the vertical line test and it's no longer a function. So if the bottom one is filled here, then the top one has to be empty. Similarly, over here we have the top one is filled, so the bottom one has to be empty. Now the fact that the circle here is empty just means that we're excluding x equals 2 on this third rule, and you can see that. X has to be greater than 2 over here. If x is equal to 2, you don't use this rule, you use the previous one. So if x is equal to 2, you don't use the y equals x line, you use the y equals 3 line. So that's what we mean when we say be careful about overlapping. Can we identify the domain and range from a graph? Well, you can. It's not always obvious what the numbers are, but you can usually get a good idea. So for example, in this picture, the domain is all of the allowed x values. And you can see from the picture that the smallest x value is -1. The largest x value is not 2, because look, we're excluding 2. 2 is excluded. So that means the domain goes from -1 to 2. We include -1, but you exclude 2. We're excluding 2. But you include 1 because that circle is filled in. Now what about the range? The range are all of the output values. So the smallest output value is 0. The output value tells you how high up you are. We're looking at the y values for this. So the input values are the x values, and the output values are the y values. The output values are the y values. Y value tells you how high up you are. So you can see the smallest y value is on the x-axis. So that means it's 0. So the smallest value is 0. The largest value appears to be 4 right here. This point is 1, 4. So the largest value is 4. Now we need to decide, are we including the endpoints or not? You include the endpoints in the range if you actually achieve them as outputs. Notice that when you plug in x equals -1, you get 0. So that means 0 is in the range, so we include 0. What about 4? Well, if I plug in x equals 1, I actually get 4 as an output. So that means I'm including 4. So the range goes from 0 to 4, and I'm including those two endpoints because I actually get 0 as an output and I get 4 as an output. So that's the domain and range for this example. And we were able to just read it off of the graph. What about this one? So now we have to discuss some conventions that we have when we're looking at graphs. So when you see a horizontal line that's dashed like this usually means that it's a horizontal asymptote. When you see an arrowhead on a graph like this, what that means is that the graph is going to continue in the way that it appears to be going. On the left side of the graph, we have this dot. That means that this function does not exist to the left of -3. There's no function over here. But the fact that there's an arrowhead here means that this function continues on in the positive x direction forever. So that's what that arrow means. But it's never going to cross this horizontal asymptote. So that gives you a bound on the output. So let's look at the domain first. The domain. Well, the smallest value in the domain, the smallest x value is -3. The smallest x value is how far to the left you can go, and that's here. That's as far left as we can go. But for the right, we can keep going forever. That's what this arrowhead is telling us. It tells us that we're going to keep going right forever. So it's going to go from -3 to infinity. Now you can't include infinity. That's not a number. But you can include -3. Now I know that I'm including -3 because the circle here is filled in. If this circle was empty, if it was an unfilled circle, then I would not include -3, and then this would be a parenthesis instead. Okay, well, what about the range? The smallest y value is -1. The smallest y value is how far down you can go. And how far down I can go is right here. Let me try that again. Let's just change the color here. Do it something like this. There we go. So the smallest y value is how far down I can go. And how far down I can go is -1. Now I'm including -1 because there's actually, when x is equal to, so if this is y equals f at x, then you can see that this point right here, which has coordinates -3, -1, that tells us that f at -3 is equal to -1. So -1 is actually in the range, so that means we use a bracket, comma. Well, what's the biggest it can be? Well, it is approaching 2, but it never actually gets there. So we use a parenthesis here. Okay, so we use a bracket for the -1 because there's actually an output value that is -1. However, there is no output value that gives you 2. You can get as close as you want to it because this curve is increasing slowly, getting closer and closer and closer to 2, but it'll never actually get there. Any value between -1 and 2, there actually is some output value that equals that. So any number between -1 and 2, you can find some y value. So for example, if I just pick, this is my y value here, then this is my input value right here. So for every number between -1 and 2, there is some x, which is an input that will give you that as an output. However, there is no input that will give you 2. So there is no x such that x will give you 2 as an output. So there is no x such that f at x equals 2. So that's why we exclude it from our range. So x equals 2 is not in the range, or y equals 2 rather. Let me just fix that 2 again. So 2 is not in the range. So that's why we use a parenthesis here to indicate that it's not in the range. So here I just mentioned those graphing conventions that I already said. So it is common to use a dashed line to denote an asymptote, although that isn't always done. It doesn't always have to be written that way. If the graph has an arrow, that usually means you should assume that it is continuing in the same direction forever after, even after it leaves the view in your graph. Now, it isn't always easy to tell what numbers actually are from a graph, but the graph can give you an idea, even if it can't give you for certain. So I look at this horizontal asymptote and it looks like it's at 2. Now I don't know for a fact that it's at 2 unless I have more information, but it looks like that from the graph. So the graph gives us an idea of what the domain and range are, even though sometimes it can't be exact.